Hi, class. Um, we're going to go through the text. We're going to cover 2.1 and 2.2 in this lecture today. Early ideas in atomic theory and evolution of atomic theory. We really get into the meat of chemistry with 2.3. I don't want to devote sufficient time to that. So we begin. This picture shows a person taking a breath test and mass spectrum of their breath. A mass spectrum makes a molecular beam out of the species, ionized, and then shoots them through a vacuum with a magnet, and they form a curved path, and depending on their mass, they strike the detector in different places. And so this is an example. You've got water here and carbon dioxide here and nitrogen here. And the two molecules that are kind of strange are this one, which is methyl ethyl ketone, paint thinner, essentially, and this one, which is benzaldehyde. Benzaldehyde is found in preserved cherries, the cherries that are in a jar called maraschino cherries. It's also the smell of almond extract. So the two kind of smell the same. Okay. Early ideas in atomic theory state the postulates of Dalton's atomic theory. Use postulates of Dalton's atomic theory to explain the laws of definite and multiple proportions. The concept of the atom was first proposed by the Greek philosophers Leucippus and Democritus in the 5th century BC. Atomus, a term derived from the Greek word indivisible. Of course, we have divided the atom, but as far as an element is concerned, the smallest unit of an element is an atom. Later, Aristotle and others believed that matter consisted of various combinations of the four elements: fire, earth, air, and water. Of course, this was the early periodic table of the elements. It turned out that this theory was wrong. The philosophers also had a fifth element, or the quintessential, quint meaning five, essential element, and that went by the philosopher's stone, or which would either turn lead into gold or make you live forever. And there was a movie, The Fifth Element, which proposed that the fifth element was love. Okay, in 1807, English school teacher John Dalton proposed his atomic theory. Dalton's atomic theory. Dalton's atomic theory can be summarized in 5 postulates. Matter is composed of exceedingly small particles called atoms. An atom is the smallest unit of an element that can participate in a chemical change. I just want to add to this that molecule, in some cases the molecule is an atom, but in most cases it isn't, is the smallest unit of a compound, or of a substance, I should say. An element consists of only one type of atom, which has a mass that is characteristic of the element and is the same for all atoms of that element. This is one of Dalton's hypotheses that we have found not to be true, that you can have atoms of a given element that have different mass. They vary. We'll talk about electrons, protons, and neutrons in the future, but I'll tell you right now they differ in the number of neutrons and are called isotopes. Iso meaning same and tope meaning place, so the same place on the periodic table, but they're different. So However, the way we use this is that we usually assign a average element to the natural abundance of isotopic mixtures. And so we use it this way, that we assume that the element consists of only one atom type, which has a mass, a characteristic of that element. What determines the chemistry of the elements is the electron shell, and that remains the same between the isotopes. Okay, atoms of one element differ in properties from atoms of all other elements. A compound consists of atoms of two or more elements combined in a small whole number ratio. In a given compound, the number of atoms of each of its elements are always present in the same ratio. Atoms are neither created nor destroyed during a chemical change, but instead rearranged to yield a different type of matter. Copper. A pre-1982 copper penny, they say that because after 1982 they made a zinc core that they coated with copper. Okay, contains approximately 3 times 10 to the 22nd copper atoms. Several dozen are represented as brown spheres at the right, each of which has the same chemical properties. Copper oxide is a powdery black compound. Results from the combination of two types of atoms, copper and oxygen, in a 1-to-1 ratio. When elements, copper, shiny red-brown solid, shown here as brown spheres, and oxygen, a clear and colorless gas, shown here as red spheres, react, their atoms rearrange to form a compound containing copper and oxygen, a powdery black solid. Dalton's atomic theory provides a microscopic explanation of the many macroscopic properties of matter that you've learned about. If atoms are neither created nor destroyed during a chemical change, then the total mass of matter present when matter changes from one type to another will remain constant. This is a consequence of the law of conservation of matter. We have starting materials, which we represent with balls or atoms, and they combine to form a compound, products of the change. Actually, they're not representing the conservation of matter here because there would be 2 of these produced. There's no indication of the 2. Starting material, you got 2. This would be like, chlorine exists as diatomic. This would be like oxygen and chlorine combining, and you producing chlorine dioxide. So this case does show the conservation of matter. You've got 6 balls over here and 6 balls over here. Law of definite proportions, or the law of constant composition. All samples of a pure compound contain the same elements in the same proportions by mass. So that's just saying that the definition of a pure compound is that it's found in the same proportions of elements no matter where you find it. On the other hand, it so happens if you've got sugar here and sugar there, if you've got sugar in Outback and sugar in McDonald's, they're going to have the same amount of elements, same proportion of elements within them. So isooctane. So you've got, take several samples. Now, the amount of carbon and hydrogen you find, this is like extrinsic properties. It depends on the mass that you start with. And so in the first sample, 14 grams of carbon, 2.78 grams of hydrogen. But when you take that ratio, you get 5.33 grams of carbon to 1 gram of hydrogen. But you take a second sample, the numbers here are going to be completely different. But when you take the ratio, you get exactly the same ratio, or at least within experimental error. Again, you take a third sample. These numbers are completely different. But you take their ratio and you get the same ratio of carbon to hydrogen within experimental error. This is something that led credence to Dalton's theory, but the next one led even more credence to it. And this is the law of multiple proportions. So there are many compounds that use the same two elements. I mean, if you just look at hydrocarbons, you got methane and propane and butane and benzene and all sorts of stuff. Hundreds of organic compounds that are composed of just carbon, hydrogen, and that's it. This says that when you have these compounds that are made from two elements, that a fixed mass of one element will react with masses of the other two elements in a ratio of small whole numbers. So in this case, they're using copper 1 chloride and copper 2 chloride. What you have here is that the ratio of chlorine to copper in one divided by the ratio of chlorine to copper in the other is a ratio of small whole numbers. This led to the idea that in this case, what's missing from the understanding of chemistry here is the weight of these atoms in order to count them. But when you're referencing it to the weight of another atom in the compound, then you can get the ratio of the amount of chlorine in this compound and the amount of chlorine in this compound, and it being in small whole numbers is indicative that things are changing by atoms. This was how we knew, or how we suspected, that chemistry was composed of, the chemistry of compounds was composed of atoms reacting with one another. Compared to the copper chlorine compound in A, where the copper is represented by brown spheres and chlorine by green spheres, the copper chlorine compound in B has twice as many chlorine atoms per copper atom. Let's see. This has got 1, 2, 3, 4, 5, 6. This has got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, I'll just believe them. Evolution of atomic theory. Outline milestones in the development of modern atomic theory, summarize and interpret the results of the experiments of Thomson, Millikan, and Rutherford. Describe the three subatomic particles that compose atoms. define isotopes, and give examples for several elements. What are atoms composed of? Is there something smaller than an atom? Here we will discuss some of those key developments. Thomson experimented with cathode ray tubes. A cathode ray tube is a sealed glass tube from which almost all the air has been removed. It contains two metal electrodes. When a high voltage was applied across the electrode, a visible beam called a cathode ray appeared between them. Regardless of the metals used, this beam was always deflected towards the positive charge and away from the negative charge. Thomson was able to calculate the charge to mass ratio of the cathode ray particles. The cathode ray particles were much lighter than atoms. The particles are negatively charged. These particles are indistinguishable regardless of the source of material. The cathode ray particle is what we now call an electron, a negatively charged subatomic particle with a mass more than 1,000 times, I don't like that phrasing, with a mass less than 1/1000th that of an atom. Thomson produced a visible beam in a cathode ray tube. This isn't, by the way, the most common cathode ray tube was the old heavy television set that we used to use. So that projected the beam by hitting the face with the cathode ray. This is an early cathode ray tube invented in 1897 by Ferdinand Braun. In the cathode ray tube, the beam, shown in yellow, comes from the cathode and is accelerated past the anode towards a fluorescent screen at the end of the tube, just like a television set. Simultaneous deflections by apparent electric and magnetic fields permitted Thomson to calculate the mass to charge ratio. Escape. Bump. I gotta take a break. Okay, I'm back. Simultaneous deflections by applied electric and magnetic fields permitted Thomson to calculate the mass to charge ratio of the particles composing the cathode ray. This was important to understanding electrons and protons. Okay, the discovery of the electron. There was another part. There was a very careful experiment done by Robert Millikan called the oil drop experiment. And he was able to actually measure the charge on the electron. He created these microscopic droplets basically by spraying oil. And you really didn't have to do anything. Just the act of spraying it with a plastic tip or whatever, it created electrical. Some drops had different charges of electricity on them, and they slowly sank in the air. The air being a viscous fluid, so it's just like little drops of mist. They're just slowly falling in the air. Of course, the air in his container would be perfectly still. Now, he could look through a microscope and bright light, of course, to highlight those little droplets, and he could impose an electric field on these drops, and he could stop their descent by cranking up the electric field. He can actually reverse, make them go upwards as they were repelled by the bottom electrode and attracted by the top electrode. And he could balance these falling in gravity with an electric field. And by that way, he could measure the force that was exerted on that tiny droplet. If he knew the size of the droplet, he knew its weight, and he knew what the force, the electric field on that was, it allowed him to determine what the charge on the droplet was. And what he found, let's say, Millikan's experiment measured the charge of individual oil droplets. I mean, this is a mist. The tabulated data are examples of a few possible values. Okay, so he had spray. It's like what you'd use on a perfume bottle. He'd spray the oil droplets in there. Sometimes they would shoot them with X-rays in order to increase the charge on the droplets. And as they fell through here, this was a microscope. It says telescopic, but it's a microscope looking at the mist particles. He could change the voltage on this electrode and this electrode in order to have them be hovering in the middle. Charged oil droplet under investigation, observation, electrically charged brass plates. And these are the various charges that he would observe based on the voltage necessary to get them to stop drifting downwards in the gravitational field. And so sometimes he'd have values that were the same, but oftentimes with each experiment things would be different. But this was the key, is that they were always charged in a step. Either, 4 of these, 3 of these, 5 of these. It was this was the value between different charges. So if we go backwards, take this one minus this one, it's that 1.6 times 10 to the minus 9. This one minus that one, that's 1.6 times 10 to the minus 9. So 19th. So anyway, this was the charge on a single electron. Now this is critical because this is how we know about what we're going to talk about, Avogadro's number, is that once we know that we're transferring electrons to do a chemical reaction, like electroplating, we can know how many coulombs of electrons we send through there, and therefore we know how many individuals we sent, individual electrons, and from what we know of the chemistry, we know how many electrons are necessary in order to complete one metal atom to be deposited. Okay, Thomson already showed that the charge to mass ratio of an electron to be this, and so now we knew the two most critical things: the mass, the charge, and from the charge to mass, we knew the mass of the electron. And it was 9.107 times 10 to the minus 31 kilograms. Thomson suggested that atoms resemble plum pudding. Basically, everything, it's essentially like we now understand the sodium chloride to be big balls of electrons and big balls of protons, all just stuck together. But there were other experiments. It says here Nagaoka, now Nagoka, he proposed that the atoms had a nucleus with the electrons surrounding them. I don't know what data he was responding to, but the next slide is going to be about the Rutherford experiment that confirmed the Nagaoka structure. The discovery of the nucleus, Ernest Rutherford. Ernest Rutherford's gold foil scattering experiment. He aimed a beam of alpha particles at a very thin piece of gold foil. Alpha particles are positively charged. The scattering of these alpha particles was examined using a luminescent screen that would glow briefly when hit. If you're doing this with an individual alpha particles, you probably will not want to sit there and look at it, at the scintillations, but rather have photographic paper at all the stations around it, and they would accumulate the scintillations that would occur. But here's the ring around the sample. This is the gold foil. Here you have a highly radioactive substance in a lead block, and this is a tube cut out in the lead block, and the radioactive source is at the back of the tube, and this makes a gun of alpha particles because it's the primary source of primary means of decay of this radioactive material. And it goes and it hits the aluminum foil, and most of them go all the way through. However, of all the others, there's a lot of scatter, even backscatter. The backscatter is what's so strange. If the center of the nucleus had been light, then a alpha particle would at worst hit it head on, and then the two of them would go off in towards the screen in the back. But the fact that alpha particle bounced off of something, and something much more massive than it. So this suggested, it says here, Geiger, of the Geiger counter fame, and Rutherford fired alpha particles at a piece of gold foil and detected where those particles went, as shown in this schematic diagram of their experiment. Most of the particles passed straight through the foil, but a few were deflected slightly, and a very small number were significantly deflected. The volume occupied by an atom must consist of a large amount of empty space. So the number of scattered were like 1 in 1,000. Almost all of the atom is empty space, but the part that's not is a small, relatively heavy, positively charged body. The nucleus must be at the center of each atom. The nucleus contains most of the atom's mass. That's why the alpha particles could bounce off of it. Negatively charged electrons surround the nucleus. If the nucleus had been positive, the alpha particles would have stuck to it. The proton, a positively charged subatomic particle, is located in the nucleus. These are the conclusions of Rutherford's experiment and how we know where these things are. The alpha particles are deflected only when they collide with or pass close to the much heavier positively charged gold nucleus. Because the nucleus is very small compared to the size of an atom, very few alpha particles are deflected. Most pass through the relatively large region occupied by electrons, which are too light to deflect the rapidly moving particles. Isotopes. Okay, now we're getting to what isotopes are. Atoms of the same element that differ in mass from others of the same element. Frederick Soddy won the Nobel Prize in 1921 for proving this, and this is a violation of Dalton's hypotheses, but not one that significantly changes the theory. Neutrons. These are uncharged subatomic particles with a mass approximately the same as that of protons. Discovered by James Chadwick in Cosmic Rays in 1932. Neutrons are also found in the nucleus. So we understand the nucleus to be composed of neutrons and protons, and the electrons to be flying around on the outside. And now we start sections 2.3. That will be for another lecture, but we will be understanding how this applies to elements and to atoms and to the symbols that we give them in the atomic mass, atomic number, and charge of an atom or ion, and what the atomic mass unit is, the AMU, and the average molecular mass for an element, and calculate the average atomic mass and isotopic abundance of given elements. Thank you very much. Bye-bye. Yep.